But then how to describe, characterize the relationship in a nonlinear model. So here we have kind of what I call quasi-nonlinear model. Later on I will talk about why it's quasi. It's not really a nonlinear, but it is. It could be viewed as nonlinear. So here we have a function y equal to x squared, right? Suppose x changes from delta 0 by x0 by delta x amount to this number. So x changed from x0 to x0 plus delta x. So how much does y change? Because here we want to figure out delta y over delta x, right? Because that captures the association between x and y. So if we replace y with x's, we have y changes from x0 squared to x0 plus delta x squared. Now we call the rise over run. That is the amount of change in y, delta y, over the amount of change in x. Sometimes we call run, very high school term. The ratio becomes, right? We're just plugging all the numbers here. So in the numerator, that's the difference between two y's, and in the denominator, that's, just delta x. So we carry through all the computation. What we get is 2x0 plus delta x, a lot of cancellation. So here, what we're trying to do is, what is the effect of x on y? So this captures the effect of x on y, because we want to figure out for a certain amount of change in x, what is the amount of change in y? And we're going to take that ratio. Okay? But the question is, what is the instantaneous effect of x on y at point x0 and y0? Because that's the starting point. That's the point we're most interested in, right? So actually, it is when delta x approaches 0. When this approaches 0, or when the change in x is infinitesimally small. This is almost the definition of the derivative at this point, x0 and y0, for the function of y equal to x squared. So again, let me repeat. How to describe the relationship between x and y at point x0 and y0, because it is nonlinear, and along the curve, the relationship changes. Later on, I'm going to show you graphically. But how to describe that? Well, it boils down to this number, right? And as delta x approaches 0, that is infinitesimally amount of change, right? At x0 and y0, that the ratio of delta x over delta y over delta x at a point very close to x0 and y0, that describes the association between these two variables at that point. That's when delta x approaches 0. And that number is actually 2x0. And that is actually, the derivative. Later on, you'll learn that derivative of this function y equal to x squared. Okay, at point x0. And that's also called the instantaneous effect of x on y at point x0 and y0. Why instantaneous effect? Because that only captures the effect of x and y at that point. Once the point moves on to the next one, okay, then that is not going to be the effect. Okay, it's going to be a different effect. So let's look at the graph. The green line basically corresponds to the function y equal to x squared, and this red line is a tangent line. And when we say a tangent line to certain function, basically the line touches a function curve at a certain point. So this line, the red line, is a tangent line of y equal to x squared at this point, when x is equal to 2 and y equal to 4, right? And the black line is how we capture delta y over delta x. So here I'm going to say, well, along this curve, I'm going to move x by 2 units. What's going to be the value for y? Well, y is here, right? So when x from is 2, okay, then y equal to 4. But let's increase x by 2 units. Excuse me, 4 units, reaching 6. Y becomes 36, right? 36. The difference is what? 32. The difference in y is 32. But let's say, well, if we decrease delta x, because delta x is 4 here, right? And the definition says, well, or the concept says, well, if we decrease delta x to let delta x approach 0, so it's going to be a very, very small number. It's going to be here, right? Because I want to figure out the effect of x on y just on the point or very close to the point of x equal to 2, y equal to 4. This point here, that would imply I'm going to decrease delta x to a very, very small point, very, very close to the point of x equal to 2, y equal to 4. So let's say very small here, okay? And that's actually going to be equivalent of the tangent line, the slope for the tangent line, tangent to y equal to x squared. Here, the black line describes the effects of x on y when we increase x from 2 to 6. So when we say, well, if we increase x to 6, what is the effect of x on y? Well, y increased by 32 from 4 to 36. But that is not the answer we want to have, right? The question is, what is exact effect of x on y at point or in very close proximity of x equal to 2, y equal to 4, around that point, very close to that point. Well, that turns out to be equal to 4. Equal to 4, because we're going to draw a tangent line. On that point, cross that point, but tangent to the curve of y equal to x squared. So the slope of this line represents, that is 4, represents the effect of x on y, the effect of x on y for the function of y equal to x squared at a certain point. Always, why we are interested in the instantaneous effect of x on y at a certain point? Because at every single point, the effect of x on y is different, right? When we increase the axis, along this curve, we will see that the effects becomes greater and greater, right? The curve changes greater, right? When x is small, when x is small, actually, the effect is small, right? X changes, 1 unit here, let's say 1 here, this point. When x equal to 1, y equal to 1, it does not change that much, the curve, right? When x increases, actually we can see that y also increases much faster, at a much faster rate. So the effect of x on y varies with the values of x. And that shows the effect of x on y. And that is related to what we want to call derivative. So the effect of x on y actually is equivalent of first partial derivative when we talk about multivariate analysis if we have multiple predictors and one single response variable. Okay?